Welcome to 20EC703L Embedded Laboratory. Today we are going to see the first experiment. Before that, we have to know why you have to study this lab. So that is the main thing. You have to understand the basic building blocks of ARM7 processor and learn how to interfacing the various devices such as ADC, DAC, PWM, LED. So in this also we are going to interface the stepper motor and then temperature sensor also. So and also you have to analyze the performance of processor by interfacing keyboard, display and also various sensors. And also we are going to evaluate the inter performance of comparing the ARM processor and FPGA kit. So FPGA kit, it is for your VLSI design subjects and roles. We are using this FPGA processor. And finally, that apply the knowledge of interfacing between the ZigBee protocol with ARM processor. So outcome of this subject, we are going to design a ARM for specific application of the way of basic building blocks of embedded system and implementing the various of interfacing mechanism and observe the performance by using Keil software and analyze the performance of ARM processor by interfacing keyboard, display, motor and sensor. So evaluate the performance based on Keil software only. We are going to comparing that ARM and FPGA processor and interfacing the knowledge ZigBee communication protocols are IoT modules. The first experiments we are going to see here, study of ARM evaluation system. So this is the first experiment we are going to see here. The basic things in this first experiment, we are going to see the basic building blocks and then what is the communication protocol and how many ports you are using in this ARM7 embedded system and also what is interrupt, how this interrupt is activating into the ARM7 board and all. The first thing, the main apparatus required of software, it is the Keil Mu 4.1 version and also the flash match. The basic things, you have to done a program in the Keil Mu 4.1 version and afterwards you have to create that X file. That X file is going to be used in the flash matching. With the help of the USB cable, that X file will be communicating throughout that your ARM7 board and finally see the output in the ARM7 board. So this is the main working of this total ARM7 board. So before enter into that interfacing and all, we have to know that basic building blocks and all. So this ARM7, so ARM7 development board having that, we having that syllabus LPC2148 microcontroller. So we are going to use this for based upon this 32-bit and also the 16-bit ARM7 TDMA. What is this TDMA? It is total division multiple interfacing. It is also that supporting for the various interfacing concept and also it occupying that high speed flash memory 32 KB to 512 KB size. And also it is having a wide memory interface 128 bit. It is occupying that and maximum clock rate of execution is 32 bit. Here there is a 16-bit thumb mode and also 16-bit ARM mode we are to use here. And also here there will be using a three communication protocol, that is UART, SPI and I2C. So this is the main communication protocol you are going to interfacing with all the sensors. Without this, we cannot use to communicate that to that particular devices. So what is mainly a UART, SPI and I2C? So I2C is having a 400 kilobits, maximum 400 kilobit. The speed of execution is going to be used in this ARM7 board. SPI, it is having the only that 128-bit kilobit. It is going to be used the speed of execution there. So this is the main difference between that your I2C and SPI. So mainly I2C, the last say for an example, we having a totally 8 bit. So the last bit, it is going to be sending that information as a empty. The remaining 7 bit, it is occupying all the data. It is going to be transferred. And also after that receiving that information, they are providing that acknowledgement to the transmitter. But SPI having that only that buffer informations only. So there is no acknowledgement of receiving that information. So this is the main difference we are going to see in this SPI and also I2C. The next, this is the kit we are going to see here, embedded system, and what is the futures of this embedded system means mainly the it is having that flash memory and also it is having that 16 to 32 bit ARM7 TDMA. It is a USB 2 full speed compliant device controller with 2 KB of endpoint RAM. One or two 10-bit ADC provide a total of 16 to 14 analog inputs. So single 10-bit DAC provides variable analog output, low power real-time clock with independent power and 32 kilobit clock in. So this is the main of this futures and applications. It is going to be used in a general purpose, embedded soft modem, communication gateway, industrial control. Now we are going to see that architectural overview. So this architectural overview can support that ARMBA. That is ARMBA is nothing but advanced high performance bus to interface an intercontroller. And next one APB is a ARM peripheral bus for connection of on-chip peripheral functions. So the order of the bit, it is going to be used a Little Indian byte order only. What does that Little Indian byte order means? From the LSB to MSB, that is least significant bit to most significant bit order only, it is going to be enter all the data. Here there will be not using a big Indian. What does big Indian means? It is the most significant bit to least significant bit. So these two differences you have to analyze that. And also that all peripherals it allocated 2 megabyte range of address. So this is the main block diagram of the LPC 2148. Okay. So this is as far as I told that it is having that ARM7 TDMA, yes. So it is nothing but told in the division multiple interfacing. Yes, interface. So here there is occupying that SRAM and flash memory. So this flash memory up to that 512 KB size, it is going to be occupying that into that ARM7 processor. So on the list of various communication protocols, I2C, SP8, and also UART. So these are the list of various communication protocol. And also we are having a low power real-time clock, watchdog timer. So what is watchdog timer? If there is any interrupt occur in this program means we have to easily reset this entire program, and also it is coming under that starting of the program. So wherever that program has to be interrupt, it is easily reset that. That is called as a watchdog timer. And then from the left hand side, we having A to D converter and D to D converter, general purpose IO and PWM. And we have a system clock. So this is the main block diagram of the entire your LPC 2148. So this is the main thing. We are going to see the entire of your block diagram. So all of you have to draw this block diagram in your observation now. The next one. So this is a pin diagram of the entire of your ARM7. So here we are having a port 0 to 1. So here we are using that port 0 and 1 only. So all the entire connections, whatever we are seeing in that block diagram, that is going to be connecting in this port only. Say for an example, port 0.14 means this external interrupt will be connecting here. And then say for an example, your 0.10 means your RTS will be connecting here. And then say for an example, P 0.8 PWM will be connecting here. And remaining that you're having a crystal oscillator, reset pin, real-time clock. So these and all having a separate port. So this also you have to write. And finally, we have finished this entire study of ARM evaluation system. So this is the main thing. We are going to see that entire of your ARM evaluation system. So how we are going to communicate, what is that into that program? After that program, how you are going to communicate your ARM7 board? And what is that architectural overview? And what is the pin diagram? So these are all the sections we are going to discuss in this entire study of ARM evaluation system. I hope all of you understand this study of ARM evaluation system. Thank you.